All of the nonlinear oscillators that we're going to look at in this chapter are going to be in continuous time and with second order dynamics. We're going to start off with something simple. We're just going to look at the pendulum. Now, when I say we're going to work with the pendulum, what I don't mean is the simple harmonic oscillator that we have looked at in the past. That's a linear approximation to the full nonlinear pendulum. That is what we're going to be doing. Consider a pendulum that is on a rigid rod, and we're going to let theta be the angle that that rod makes with the downward pointing vertical. This theta is going to be in the circle S1. It is a circular variable. That's going to be important to us later. The second order continuous time dynamical system that defines the motion or the evolution of theta is the following. L squared, d squared theta dt squared, that is the second derivative, is equal to minus mgl sine theta. Here we have a bunch of constants. We have m and l and g. This is the mass and the length and the gravitational constant, all that stuff, whatever, positive constants. Now, importantly, this model assumes that there is no friction in the pendulum. That's going to be important to us later. All right, then, let's do what we do. Let's convert this to a first-order nonlinear system. We're going to do so by introducing a new variable, v, that is the derivative of theta. Physically, this is the angular velocity of that pendulum. With these two variables, theta and v, we can rewrite this system as the derivative of this vector, theta and v, is what? Well, the derivative of theta is by definition v. And the derivative of v is the second derivative of theta, which from our governing equation gives us minus g over L times sine of theta. Now, of course, our next step is to set this equal to 0, solve for the equilibria. There are two conditions that have to be satisfied. The first is v must be equal to 0, and the second is that, let's see, g and l are positive constants, so sine of theta is equal to 0. That means theta is what? Well, theta could be 0, or it could be plus pi, or minus pi, or plus 17 pi. There are all kinds of solutions, but remember, theta is an angular variable, a circular variable. That means plus pi, minus pi, it's all the same. In the end, we have two equilibria, one at 0, 0, and one at plus or minus pi, 0. Next up is classification. The right-hand side of our dynamics, our function f, is v and minus g over L sine theta. Taking the derivative of that gives us the 2 by 2 matrix, whose first column is 0, and then minus g over L cosine theta. And then the second column, the partials with respect to v, are simply 1, 0. With that derivative in hand, we can classify each of the equilibria. At 0, 0, we have what? We have trace 0, and determinant is positive. That means we have a center at the origin. Oh, wait a minute. I'm not sure I trust that this is a center. Not really sure on this one, but let's keep going. At the second equilibrium, at 0 plus or minus pi, well, the trace of the derivative, that's still 0. But now when you evaluate cosine theta at plus or minus pi, we get -1, and that means our determinant is negative. And now we have a saddle point at that equilibrium. Okay, so we've got a maybe center and a saddle, but let's think in particular about that center at the origin. I claim that this is really a conservative system. There is an energy functional that is preserved over time. This energy functional is given by h equals 1/2 v squared minus g over L cosine theta. The idea is this is a system that has no friction in it, so the energy is conserved. If you think about this center as what's happening when the bob is at the bottom and it just rocks back and forth, if there's no friction, yeah, it kind of makes sense that it's a true center. Now, how do we prove this claim? Well, you can prove this claim by computing dH/dt using the chain rule and showing that this is equal to 0. And once you've checked that, then you can conclude as a corollary that the orbits of this dynamical system in the theta v plane are really the level sets of this function h. And 0, 0, this center-like thing that we found, is really a local min for this energy functional. That means that it's going to be surrounded by little closed orbits. This is really a true center. All right, that's it for the local analysis at the equilibria. Now the big question is, how does it all fit together? Let's take a look. If you plot the flow lines of many initial conditions in the theta v plane, then a couple of things really stand out. First of all, you can see that nonlinear center at the origin. That is really clear. You can see the conservative nature of the dynamics. What's a little bit harder to parse is the saddle point at plus or minus pi, comma 0. Because of the way this is drawn, that point is split up in two, sort of half on the left side, half on the right side. But because theta is a circular variable, you need to think about those two as being on the same point. Maybe wrap this entire screen up into a cylinder. That would be helpful. It's really worth thinking about all the different orbits that you see here and registering what they correspond to in a physical pendulum. I will leave that exercise up to you.